Hi everyone, it is my pleasure to introduce to you today Maria Petronikolou. She finished her PhD back in November at the School of Applied Mathematical and Physical Sciences of the National Technical University in Athens. And she's currently conducting postdoctoral research at the Cosmology Group at the National Observatory, still in Athens. And today, she will be talking to us about addressing the H-node tension through scalar-tensor and bi-scalar-tensor theories. So please, Maria, feel free to start whenever you want.
Thank you very much. Thanks again for the invitation to talk to you today. I'm going to present you our work on addressing the H-node tension through scalar-tensor and bi-scalar-tensor theories. An overview of my talk. I will briefly discuss on the ΛCDM model and current tensions in cosmology. Then I will focus on the H-node tension and approaches to resolve it, and I will present to you our work on the alleviation of the H-node tension through the scalar-tensor and bi-scalar-tensor theories and our results. So, the ΛCDM model, i.e. the cosmological model we have today, is characterized by the presence of the cosmological constant lambda and cold dark matter. The universe is assumed to be homogeneous and isotropic, while the underlying gravitational theory is general relativity. The ΛCDM model plus inflation has successfully described the evolution of the universe at both background and perturbation levels. However, we face some open issues, such as the cosmological constant problem, the origin and properties of dark energy and dark matter, the exact mechanism for inflation, the non-renormalizability of general relativity, as well as observational issues regarding the H-node tension and the sigma-8 tensions. So, the H-node tensions is actually the discrepancy in the Hubble constant measurements as estimated by the cosmic microwave background at the early universe and local measurements of distances and redshifts using model-independent approaches. Today, this tension is about 5 sigma. In the literature, we can find several approaches for addressing the H-node tension. So we can classify the solutions proposed in the literature regarding how we're going to treat the comoving sound horizon RS or the angular diameter distance in the expression of the angular size of sound horizon. If we choose to affect RS, we get the early time solutions, which include early dark energy models, neutrino self-interaction models, interactive dark energy, decaying dark matter models, etc. If we choose to alter the angular diameter distance, we get late time solutions, including holographic dark energy models, late modified gravity models, negative dark energy, and running vacuum models, of course, many more. In this talk, I will focus on late time solutions, since we're going to use modified gravity in order to see if it's possible to alleviate the tension through scalar tensor theories and bi-scalar tensor theories. So I'm going to study late dark energy models. So that's why I'm going to point out now mechanisms that could lead to the alleviation of the tensions. For late dark energy models in the literature, we can see that they must exhibit first phantom behavior, which means that the equation of state parameter for dark energy models should be lower than -1 for some redshifts, and that will lead to faster expansion. Or the model should obtain a weaker gravity, which means that the term G effective over G should be less than 1 for some redshifts, which leads again to faster expansion. So we're focusing in scalar tensor theory, specifically Hortensky gravity, to see if it is possible to alleviate the tension through the H-node. This theory is was introduced by Gregory Hortensky in 1974. Hortensky gravity is equivalent to generalized Galilean theory. Is the most general four-dimensional scalar tensor theory with second-order field equations, and it's free from Ostrogradsky instabilities. The Lagrangian that is describing this theory with an extra propagating degree of freedom, is given by the equation 1 with the combination of 2, 3, 4, and 5. Here you can clearly see the dependence of these terms on the functions of k and gi, with I running from 3 to 5, which are depending on the scalar field phi and its kinetic energy x. The total action of the theory is given by equation 6, where the term Lm accounts for the matter content of the universe, which corresponds to a perfect fluid. Now we were going to consider an expanding universe, which is described by a flat and homogeneous anisotropic geometry, FLRW. So we use the metric given by equation 7. If we vary the action that I already present with respect to the metric, we can obtain the generalized modified Friedmann equations in the framework of Hordensky gravity, equations 8 and 9. Again, if we vary the action with respect to the scalar field, we obtain the equation of motion for the scalar field, equation 10, where the terms j and p phi are given by expression 11 and 12. Now we're going to focus on how this framework is going to alleviate the H-knot tension. So I will present our work with Vasilakos and Saridakis on that. So what we did was to define the pressure of matter to be 0. So we have dust matter. We choose to work on cosmological redshift as our independent variable, and we set the k function to depend on the kinetic energy of the field and simple scalar potential, which is given by this expression here. What we want is to construct suitable subclasses of the theory in order to obtain a behavior that is almost identical with that of the lambda CDM at early times, so at high redshifts, and we need to have a deviation from lambda CDM at late time, so at low redshifts, from that of the lambda CDM. So we set again G3 term equal to 0, the G4 term constant, and we choose to modify each time in order to construct the subclasses. The G5 term, which we set it to be shift-symmetric, and also it's the non-minimal coupling term of the theory. So we construct 3 subclasses. In the first actually, the G5 term depend on the x square. The second class we have dependence of actually a quartic dependence of the x kinetic energy of the field, and finally we have G5 as a function of the previous models. We need now to secure that the initial conditions we choose will lead to what I said before. I mean the almost identical behavior of our model with that of the lambda CDM at early universe. And of course, we need to obtain that the density parameter of matter today is closer to 0.31. So we solve numerically the Friedmann equations and we obtain solution for the Hubble parameter. Now I have to remind to you that the Hubble rate for the lambda CDM model is given by equation 13, where the H0 is measured by the Planck collaboration, and it is equal to 67.27. So here are our results for the first class we constructed, where the G5 has a quadratic dependence of the kinetic energy x. We see through this plot of the normalized Hubble parameter as a function of the redshift that indeed at the early universe our model is identical to that of the lambda CDM, since we introduce late time deviations. And for several values of the C parameter here, we see how our model evolves through time. With the black line, we see the lambda CDM model, and at late time, we see that our model could achieve an alleviation of the tension, and specifically for the parameter value of C equal to 1.3, the H0 is around actually 74 kilometers per second per megaparsec, which is in agreement with the direct measurements. For the second class we constructed, with G5 having a quartic dependence of the kinetic term, we see again almost the same behavior with the previous model. And again, at the late universe, we have an alleviation of the tension, specifically for the lambda value, the lambda parameter value equal to 1, we get the H naught to be close to 74 kilometers per second per megaparsec. And finally, the result of the last case, where we have the sum of the previous two cases, we see that, again, at the early universe, we have no deviation from the ΛCDM model, while our model for several values of the lambda and c parameters obtain a deviation on the late universe and an alleviation of the tension for the case where the lambda is equal to 0.02 and c is equal to 1.3, which is again in agreement with the direct measurements for the H naught. Now, what is the mechanism that led to that alleviation? We know that in Hortensky theories, the G effective over G term is given by equation 14, which clearly shows us the dependence of the G5 term that we modified. So we plotted that term as a function of the redshift for every case. Here I present to you for the first model the result we obtained. And what we see is that this term exhibits a decrease at intermediate redshifts, which means that this model appeared to give a weaker gravity that leads to faster expansion, which is a mechanism presented in the literature. Of course, we needed to secure that our solutions are stable. So we checked the conditions about the scalar field propagation and the tensor field propagation speed to be greater or equal to 0. And here I give you the plots we obtained for the first class and specifically for the parameter choice C to be 1.3. And as we see, the conditions are holding, so our solutions are stable. Finally, in order to complete our analysis, we confronted our models with observational data. In the left, you can see a plot of the distance modulus as a function of the redshift with the Pantheon dataset and the lines that corresponding to the first model we study and the second one. And with a black line, you can see the ΛCDM model. And here you can see that we have achieved the correct observational behavior, cosmological behavior, and we are in agreement with the Pantheon dataset. While on your right, you can see a plot of the Hubble parameter as a function of the redshift. And here you can see the confrontation of our model with the cosmic chronometer dataset. And here at the confidence level of 3 sigma, our models are in agreement with that dataset and could give a higher H naught value than that of the ΛCDM. Now, I'm going to talk about bi-scalar tensor theories, another category of modified theories of gravity. Bi-scalar tensor theories are novel modifications of gravity that consists of a Lagrangian with Ricci scalar and its first and second order derivatives in a combination that leads to ghost-free theories. This theory is described by the action given in expression 15. And in that expression, we consider that the function f is depending on functions k and g, which are depending on combinations of the Ricci scalar with its first and second order derivatives. If we perform conformal transformations, we can introduce scalar fields chi and phi. So the action that I presented before takes the form 17, where the k function and g function are depending on the scalar field, and in the expression b, which again depends on the chi and phi scalar field. So we have a theory with two extra propagating degrees of freedom, the scalar fields. So we'll again assume that we're working with a FLRW metric of the form that we show at the beginning of the presentation, and by varying the action with respect to the metric, we obtain again the Friedmann equations for that case scenario, which are equations 18 and 19. And here we have the emergence of effective dark energy and the effective dark energy density and pressure are given by equations 20 and 21, which are clearly depending on the presence of the scalar fields phi and chi. Again, if we vary the action with respect to chi and phi, we can obtain the equation of motion for those scalar fields, equations 22, and 23. Now we will focus on the alleviation of the H-knot tension, a work we did with Banerjee and Sarivakis. What we did again was to create the suitable subclasses of this theory in order to introduce again late time deviations. So we made specific choices for the functions of k and g. So our first model, the model I, is depending on the k function in this way. And here we have set g to be equal to 0. The second model, we have this combination of functions. Again, we set the correct initial conditions in order to obtain late time modifications, and finally, in order to be inconsistent with the observations about the density parameter of matter today, which is 0.31. We again solve numerically the Friedmann equations and equations of motions of the scalar fields, and we obtain solution for the Hubble rate. Here are our first result for the first case, for the first model we created. Here again, you see a plot of the Hubble, of the normalized Hubble parameter as a function of the redshift. With the blue dotted line, we see the ΛCDM model, and the other lines are corresponding to our model with for several parameter choices we made. Specifically, for the parameter choice of -10, z equal to -10, we get again that the H-knot is close to 74 kilometers per second per megaparsec, so gives us the potential of the model to alleviate the H-knot tension. For the second model we constructed, we again take a very similar result. Again, we have deviations from the ΛCDM model of our model for several parameter choices of Xi. And there is an alleviation of the tension for the case where the Xi is equal to -10 and H0 is close to 74 again. For this case scenario, the mechanism behind the alleviation of the H-knot tension appears to be the behavior of the equation of state parameter for dark energy, which seems to exhibit the phantom regime, while the W dark energy is less than -1. So this mechanism of the phantom behavior leads to faster expansion. And here you can see the plot we obtained for the first model we constructed, the same behavior we obtained also for the second model. Finally, we confronted our models with observational data. Specifically, we chose, again, cosmic chronometer dataset, and we plot the Hubble rate as a function of the redshift. Again, we see that our models are in agreement with the observations of the cosmic chronometer dataset and obtain the observed cosmological behavior, leading also to H0 value higher than that of the ΛCDM and potentially alleviating the H-knot tension. So finally, if the tensions in cosmology are not due to unknown systematics, they may indicate the need to extend the standard law of cosmology. The modified gravity provides a promising framework for addressing these tensions and could probably give a wide range of theoretical insights. In this work, we explored Scalar-Tensor and Bi-Scalar-Tensor theories with reduced late time modifications and reproduce the observed cosmological behavior while we show that we can alleviate the H-knot tension. Future work, we are actually now investigating the potential of these models to also alleviate the sigma tension, and of course we are conducting observational confrontation of these models with all the available datasets. Thank you.